everybody, I'm Cristian Prevedello. I'm from Italy and I work as Chief Architect at Prevedello. Today in my session, I'll show you how we created a scalable, resilient and reactive platform based on Kafka and Kubernetes, putting together microservices written in different languages. Thank you for watching. See you.
Hello everybody and welcome to this session. I'm Cristian Prevedello, Chief Architect at Previnet, and this session is about real-time stream processing. From the schedule I see it's a popular topic this year, so let's explain something different to what you already saw. So who we are? Previnet is an outsourcing company. We work mainly with insurance and banking. We have also a division that works for pension funds, finance, and healthcare. Actually, we have 300 active projects with almost 100 different customers. We have an on-premise data center. We don't use cloud services because our contracts with other customers prevents that. And historically, we are a pure Java shop where we deployed our ACID applications on Jakarta application servers. And other than that, we have batch applications wrote in different languages, scripting languages to process our batches in a batch way. What do? We process data files that we receive from our customers. It's basically a sequential processing, and we parse these data files, HTML, XML, sorry, and CSV files, and we transform the data and we put such transformed data into relational databases. We also calculate tariffs for our insurance companies. For example, we simulate pensions plans, we generate documents. Recently, we also introduced AI and machine learning components like natural language processing, OCR, text extraction, document classification, image recognition, and stuff like that. We also use our platform to support our infrastructure. So we manage our log systems with our stream processing platform. So we collect logs and we structure such logs, we transform them, we aggregate them, and even if modern applications are, let's say, cloud native, even if we don't use the cloud, but all the metrics and the monitoring is performed through some native and dedicated components inside the application. We also have many legacy applications where we just parse the rich log that the application is producing. We also operate our security operating center, where we collect logs and events, and we trigger security alerts. What we had, which problems we had in the past? If we look 5 years ago, data was still not such big that we could manage with traditional systems. But over the time, data size increased. We got some additional customers, big customers, and these customers put on the table some more challenging service level agreements. We got some strong requests to move away from the batch way, once a day on a daily schedule, towards to a more near real-time way to react to the input we received from our customers or end users. Traditionally, we had a very synchronous and asynchronous interactions with different services and tightly coupled systems. And we had several challenges to adopt new technology like machine learning and artificial intelligence. And it was very hard to quickly scale. Let's say today we receive 1 gigabyte of data files. Tomorrow we save 10 gigabytes, 50 gigabytes. Then it was somehow much harder to scale the system, and so it involved a lengthy process with our operations guys. Maybe in the past we also had to involve the development team and so on. So what we did in the past, we tried Hadoop. We had and we still have a cluster, a Hadoop cluster, and we usually coded these jobs with Spark jobs. But even if we solved somehow some problems, that system was pretty heavyweight. It was very expensive to operate. We just had a dedicated system that was used to ATL mainly. We had problems with training because it was Scala was just used for Spark jobs, and we had to train people to use Spark and Scala. And it was troublesome to integrate into our regular applications, that is mainly Jakarta traditional web applications. What we wanted was something simple and thin that we could basically get up and running without much fuss. We wanted something that could run also our regular workloads and not just big data stuff. We wanted to integrate applications, normal and regular applications, and we also wanted something that could support our transition to microservices and domain-driven design. And we wanted something that we could plug into different technology and languages and runtimes. So what we came up with a couple of years ago, it wasn't something just related to technology or to a framework. It was something more extensive. It was a set of tools that we wanted, a set of services that was ready to be used, libraries, guidelines, and best practices. So it's more an ecosystem that was offered to our teams that could be used to develop their applications. So the solution was to wrap everything into a container. So we basically solved the operation problem to run these different technology and runtimes. We run everything on Kubernetes as a resource orchestrator, and we use Kafka to exchange messages and events. We use Kafka as a message bus where everything goes through to communicate with different microservices. We promote as much as possible asynchronous communications, interactions. In this way, we connect in a loosely coupled way different parts of the system, and we avoid that a failure basically impacts a very lengthy processing pipeline. We tend to apply data pipelines and stream processing everywhere. In this way, we can scale much better. We can sustain spikes in the traffic and requests without suffering many issues for what concerns the load of the system. But also, we support a request response style. Through Kafka, we send a message and we expect a response from another service. And of course, we break our applications into different microservices. So what we came up over several years of experiments and training and tests, it's something that here it's pictured. We have databases, that is relational databases, mainly Postgres. We also NoSQL database, that is Mongo, where we put our data. We have different types of technology stacks that we can use. We can use Kafka streams with Scala that is running on JVM. We can use also Akka-based microservices with Scala, also here on JVM. We can also plug in our platform Python-based services and something in Node. Not much popular. Indeed, we don't have much stuff in Node, but we can plug this stuff in the platform. We receive data from databases where each microservices is going to query the database, but we also receive requests from the external world through the HA proxy ingress controller. Like we said, we use Kafka to store all our messages, and we have an in-memory database that is ready to store all that stuff that can be stored in Kafka, namely binary, blobs, huge files, and stuff like that, and also to store in a temporary way all data that wouldn't be feasible to fetch and query every time an external database or Kafka itself. The platform, like we said, we have generally each service has an input request topic where it receives the inputs or requests or events. They do something and then they spit out on the output topic or let's call response topic the result, or more than one topic in some scenarios. We have different topics for batch request and real-time request. Our services can be used for traditional, let's say, batch jobs that are triggered once a day, twice a day, and so on. But we don't have any strict service level agreement on that jobs. On the other hand, some services are invoked directly from an end user, and so they want the answer right away. So let's say it's a real-time request, and in that case, the response time is very critical. So we must have a low or latency for those requests. To manage temporary failures, we have recovery topics. So if a request goes bad, let's say a microservice A must communicate with microservice B, and that request is not, the response for that request is not received within an allowed time, we put that request in a recovery topic, and so failed processing can be retried with an increased retrying time. Here again, for real-time request, it's a bit tricky, so we don't much try again many times. For batch processing, it's more easy to retry until we get it right. We use Kafka streams. So we decided to not go with Spark or structures streaming with Spark. We gave a shot in the past with Flink. But at the end, we prefer Kafka because it was the most simple tool that we could adopt, and we could train people. So we use Kafka streams that we can leverage the state store. We could use the stateful processing paradigm that is built in Kafka streams. We can easily discard duplicates with Kafka streams. And here we try to implement plain and simple stream processing paradigm. And we try to repartition as late as possible. We saw for some scenarios where eating again Kafka and repartition early could cause a lot of problems, a lot of I/O. So we tend to avoid much data transfer between Kafka and our microservices. For what concerns the typical Scala and Kafka streams-based stack, like we said, we use it mainly for stateful processing. We can use all the features like interactive queries, state store, joins, and stuff like that comes out of the box and in a very easy way to grasp and to use. It is used to orchestrate data pipelines when we need to communicate with many different microservices, and so exchange and route those requests or events. The only tool, the only framework that we found very easy to use and that is strong and that is reliable is Kafka Streams. Out of the box, Kafka Streams supports the resilience of our system, so we can leverage those features, so we don't have to think hard how we can increase the resiliency of our systems. Of course, Kafka Streams has its own problems, so it's not applicable for long-running tasks. And it's not applicable for IO bounded tasks, because inside Kafka Streams we have many timeouts, many parameters that if we don't give to Kafka an answer, the consumer is identified as dead, and then we have a rebalance while maybe the consumer is still running. So here we just have a, let's say, a very short and with more brained processing with no interactions with other systems. Here we can easily scale horizontally. We increase the number of partitions, and at the cost of network cost, we can basically scale out the number of requests that we receive. And here it's the most simple stack that we can use. Or even if we could use Kafka with Java, we decided to stick with Scala, and Scala, it's not exactly easy to learn the functional paradigm, but anyway, we found a subset of Scala and a subset of tools that we provide and frameworks where we can train people and they can use with proficiency the system. Another stack that we can use is Scala, but this time with Akka and with Alpaca for our connectors, for our connections with other systems. This stack, of course, it's more tricky. It involves the knowledge about how Akka works, actors, Akka streams, graphs, and so on. So it's dedicated for skilled developers, usually my team, the architecture team. It is used for long-running tasks and for IO bounded tasks, where we have a much greater control of what we need to communicate to Kafka when we want to communicate to commit an offset and so on. It's easily adoptable for asynchronous jobs, while Kafka API is strictly synchronous. We can't process in an easy way, or let's say in a reliable way, an asynchronous request. Flink, for example, has this one. There's a Kafka improvement pending for the same API in Kafka Streams, but we don't have that here. So when we need to scale up and when we need to process a lot of asynchronous stuff, or we need to parallel processing something without going back to Kafka, so without having a network hope, we stick to this stack. We usually have, we spin up an actor for each message that comes from the topic, and as soon as that actor or the chain of actors that are dedicated to process that request, we commit the offset to Kafka. Here we developed internally some frameworks and some libraries to ease this kind of job, but still it's still tricky, especially when it comes to the synchronous and the actor model. The most important, the key factor here is that we can parallel processing a single partition. While Kafka Streams, we can scale out, increasing the number of partitions, but then when we process a message, we must commit that message before go further. Here with Akka, we can take just one partition and process in parallel many messages at the same time, and all the stuff for committing and the guarantees are managed by Akka itself. So I would say it's a more advanced use, but it's rewarding in some scenarios. Another popular stack is Python, that is mainly used for machine learning and artificial intelligence. We use Kafka Python library. Here we had many problems in the past. Python has the global interpreter lock, so we can't scale up with threads like we do in Scala or Java. So we just have one instance per partition in a given topic, and that instance for that service has just one thread that processes the request. Usually, given that such services are heavyweight, what they process is a long running task and heavyweight. So we try to avoid to reprocess requests. So we commit very often, and we have a pretty aggressive policy to discarding, for what concerns discarding all messages. So here we are rather picky. We had the problems in the past tuning all parameters for what concerns keep alive, rebalancing, and so on. The Kafka Python library was not picking up rebalancing in the right way. So it was a very stressful moment of our introduction of this stack, but I mean, at the end, we did it. So when we need to implement a new application, we have something very specific to that use case, but many times we also have something that usually goes to a database, reads a file from a FTP server and stuff like that. So we implemented a set of connectors that are usually used for heavy IO bounded tasks, so reading from file systems, from an external service, and so on. In the market, we have many connectors available. The Confluent platform, for example, has many of them, but we wanted something more lightweight. At the end, we prefer to code our own services where we had the full control of what we could configure. And we wanted higher performance and lower resource consumption. We have some connectors that can process 1,000 requests per second, and they just consume 100 megabytes or 200 megabytes. While our experiments with other connectors in the market, we had a much higher resource consumption. We have connectors to read and write data to databases, of course, Mongo, Postgres, FTP servers, through different encryption protocols, files, of course. And we also developed some connectors to proxy requests between services that couldn't support Kafka. We have some services that we don't want or we can't just plug directly into Kafka because we don't have a reliable framework and library. So what we did was to create this Kafka proxy that, compared to other, let's say, competitors, we gave a different meaning. We don't want to simply expose Kafka stuff through a REST service, but we wanted to give to this service a higher concept. So we don't deal with this service with topics, with partitions and stuff like that. We just post a message, typically a JSON message. We could post a JSON message plus some binary files. And then this service routes the request into a topic, and optionally we can wait for a response or fire and forget. So from the consumer perspective, from the client perspective, behind this proxy, we don't know what's going on. We know there's Kafka, but we don't expose Kafka details. So it's more about a business use case than a technical use case where we adopt Kafka. Another important connector is a query agent. every time we go to a database, it's somehow troublesome to integrate this stuff in all our services. So we developed just one microservice where its job is just to query database on a schedule pattern, or if this service receive a request from another service. We queries Mongo databases and also relational databases for now. We can transform the result in one message for each request, or we can split each row. The result set can be split in each row for one message per row. It depends, of course, on the expected payload result size. So it depends what we want to achieve. And when we split a result set into one message per row, of course, there we can scale up our consumer on the other side. For what concerns Kafka details, here we are pretty easygoing. The key format is a string that is composed by three parts: a protocol version, an action, and an event and message ID. That's it. The message format is JSON. So it's far from ideal, but given that we had to bring on board many different teams, many with different speeds, and they had a very agile and fast development, so their message formats, they were not stable enough. They changed their mind here and then. So what wasn't feasible is to adopt the schema registry and enforce the schema in our topics. So what we put instead as a basic rule is the consumers must be flexible and must be able to deserialize and read whatever they come, whatever comes up in the topic. And even if at the beginning we had some issues, right now we are pretty stable on this. So based on the protocol version and the action part that is part of the key, we can usually serialize or deserialize the message that is incoming in the right way without problems. Of course, JSON is very bloated. We have a huge overhead, but for now it's okay. For what concerns guarantees, we have at least once guarantees. We don't lose messages. We prefer to have duplicates. We don't use exactly once that is coming built in into Kafka streams. This especially caused some problems with Python consumers. I don't know why. We never spent much time on this topic, because anyway, exactly once works only on a very limited number of cases. If everything works fine, okay, we can have exactly once, and only if we have a supported sync and a supported source on both ends. But when we started doing some chaos experiments, we had problems where it wasn't working. So what we do is stick with at least once guarantees, try to deduplicate on orchestrators that is managing the communication between these services. If we must be absolutely sure there's no duplicates, we must resort to an external database with idempotent writes. And when we don't want to go to an external database, what we do is at the end of the processing, put a quality gate where we can identify if the wrong results were produced. And in that case, we must reprocess from scratch. When we process a CSV file and we must produce another file with some ATL applied to the source file, writing to files is rather tricky. So we tried many different approaches, but at the end, what paid off was, okay, let's suppose everything goes fine, and that's most of the time. We don't have any interruptions of the system, but if we get an error and a consumer crashes, we know that we have to reprocess everything from scratch. A typical example of application of this platform is ATL. We receive an input request in a given topic, simulations, where we receive, you need to process, to simulate all these pension positions for these guys. So the FTP connector goes to the FTP server, downloads the zip, unzip the file, read the text file line by line, push to a topic, one record for message for each line. Then we have a Kafka streams service that is simulating all these pension positions. We put the result into another topic, and then we have an orchestrator that basically is fetching all these results, and they write to a file all the positions. To identify if we are done with the job, we use a state store where basically we increment the number of processed rows, and these stats are initially initialized with the number of expected rows, and then each time we receive a processed row, we increment the number of processed rows. And when we have that the number of expected lines is equals to the number of processed lines, we are done. Of course, we have a quality gate, because if one of these services crashes, we might have duplicates. So at the end of the processing, inside the file that is brought to the file system, we could have some duplicates, even if the number of records is the expected one. And if everything goes fine, we zip the file and upload the file to the customer FTP server. Here we are talking about several gigabytes of files and almost 1 million positions that needs to simulate it right away. And so here we could achieve to cut, we could cut the time of processing from several hours to just 10 minutes, 15 minutes. So in the right way. Another scenario is doc classification, where we have the query agent that is collecting from a relational database which documents have been inserted in that specific application. We send a message to the orchestrator. Here we get the binary PDF image or whatever it is. We get a binary blob and we put in Redis, and then we start the dance of the classification itself. We must, for example, go through a pre-processing of the document itself. So we split the document into sub-documents, one sub-document for each page. We must have to resize, adjust, rotate the document itself. Then we go through an OCR service where we text extract the stuff, and then we start the real Docker classification, where we call other services like detect if the document has an identity card, or it's a medical prescription, or if it's an invoice detect. And then the Docker classification goes through the actual extraction of the text contained into the medical prescription, or the text contained in the invoice info or extract. So at the end of the day, when everything is processed, we identified each type of documents we had in the original document. We extracted all the information from these documents. We go back to write to the results to the Postgres database. here we say it seems that all messages go through directly from a Python microservice to another Python microservice. Indeed, we always go through a Scala orchestrator that is basically routing messages as expected. Here we have an example of what we have for what concerns the number of messages and legs. We have, for this service, we have 20, 30 partitions in Kafka, and we commit very often. We have, like we said, 20, 30 instances for each service. We process 40,000 documents per day. And here we prefer to keep topics small. We don't increase the number of partitions. We prefer to bring up another stack that works in parallel, because when you increase the number of partitions, we have a lot of problems when it comes to rebalancing, scaling, and stuff like that. So we don't want to have a stream processing monolith, but we break down and we replicate each services for different sets of topics. In a similar way, we have this log management. I'm running out of time, so here it's an easier scenario. We process all the logs that we receive from our services, where we parse the textual logs, we structure these logs, we aggregate, we group by windows, we put a set of considerations where we can trigger then some alerts for what concerns our monitoring systems. We feed our OpenTSDB, TimescaleDB, or Prometheus and systems to put there some intelligence to see if everything is fine. The customer assistance platform is very similar to the doc classification pipeline, where users can book and manage a visit with a doctor. They ask some info, or they can ask for reimbursement. And here the platform is an event through event-based architecture. We send reminders, we react to user experience, user activities on their mobile applications. Here again, we have different systems that are put together and different technology used. The challenges we had was training and culture. So getting on board developers that were used to develop Jakarta Java-based applications, synchronous Java-based applications was quite challenging. So we had to invest on training, on culture, on explaining the benefits of a different approach. The problem was that we had to deal with many different people and many different systems. We don't have just one system that we can massively scale, but we have many different parts that we can plug together and connect together. So it's more troublesome to have everything up and running. Another challenge we had was getting Kafka running smoothly. In the beginning, we had serious problems where Kafka was not reliable. We had bugs, we had operating challenges. But after, again, a lot of study, investment in training and experimenting, we are pretty happy how we can scale out and we can run our Kafka cluster. Monitoring is key. If it's a train that is moving fast, loaded with a lot of stuff, and if there's a small rock on the binary, you basically have a huge crash. So we have a very strict monitoring policy. We have alerts on consumer logs. So if everything goes out of control, we are immediately alerted. What we experimented was that the weakest link is the end system, the traditional relational database systems that they can't scale up with our throughput. We had a lot of problems on developing a reliable and scalable sync connector to file. And but we are pretty satisfied with what we have. It's not ideal, it's not perfect, but it works. For real-time, low lag is mandatory, and here we are still trying to improve our systems, because sometimes in the past, now we are pretty satisfied, but still we have sometimes some problems. We have an increasing lag momentarily, and then we are delaying some requests to the end user. Anyway, we adopted a pretty fail fast paradigm. So if we don't receive a request, we don't retry for real time. And we had our problems with the application reset tool. So when we release a new version of application, if the processing graph is pretty different, we have to sort out something from our operations guys to update our Kafka. So that's it. I think I just have 1 more minute, and it was a rush. I don't see there's any question, I think. Okay. If there's any questions, we can meet at the Ask Me corner. I'll join there.